Well, looks like we can start. Welcome back. Might be a kind of a short class or small class today, rather, due to the Thanksgiving break coming up. Appreciate you making it in. And for any folks that see it over YouTube later on, I'd say you're here in spirit. So that's good enough for me. We just got through the third exam. So congratulations, folks. I'm going to start grading these on Friday as soon as I get them. And I should have it completed sometime by Saturday at the latest, I believe. It'll depend on when the testing centers send me back the exams. Occasionally, they only get them sent over, like, say, 5 p.m. or 6 p.m. on a Friday. So it's kind of up to when I get them back from the testing center. But I'll be grading the third exam as soon as possible. And just like all the others, sending them to your ISU email address. Well, that's the major announcement, getting through the third exam. Also, we have our quiz 11 due today. But because we were coming up to a Thanksgiving break next week, I felt like posting a new quiz was just not a nice thing to do. So we'll take a break on the quizzes. Doesn't feel great to have something hanging across an entire break. And we'll get back onto our next quiz next week. So for where we're at so far, we're on example 2 of section 9.6. We'll probably be working into a good amount into section 9.7. But we'll more likely than not, I think, finish this section when we come back from the holiday. Well, kind of a short set of announcements for today. Any questions at all before we get started? Okay, so let's take a look at what we did last. This was a while ago. We were on this week here. So full on week ago, our goal was to graph quadratic functions in section 9.6. And we had this information here to assist us in getting there. We like things that are written this way. If our quadratic function has this form, a constant times a group, a perfect square polynomial, x plus or minus a constant squared, then plus another constant, we say that that polynomial function is in vertex form. So what it means is the vertex can be just read off from what we see. The vertex is either going to be the highest point on the graph. That's if the constant a in front is positive, or it's going to be the lowest point on the graph if the constant a in front, a is -2 in this problem, is negative. So we had a -2 constant and made the graph open downwards. And the vertex here we found by taking the opposite of that coordinate, -3 became +3, copy the 3, 2, just went to this location, and it was the highest point on the graph. So the vertex form is really nice, but we also used other tricks. Once we have a vertex, there's a matchup of whatever that number is, h, the first coordinate, produces a vertical line, x equals that number h. So the 3 right here produced a vertical line, x equals 3, and that's the so-called axis of symmetry. All the points on the right side here are symmetric with all the points on the far left side. So when we went to write out a table of values, we also used symmetry a whole lot in this section as well to get the other values over here really rapidly. Well, this is what graphing looks like if your problem is in vertex form. Now you can imagine that someone might take this x minus 3, x minus 3, excuse me, completely expand that out, FOIL x minus 3 times x minus 3, distribute -2 inside, add 2 to the result, and what you get is something no longer in vertex form, won't look like that at all. And that's kind of unfortunate because now it's not as easy to identify where the vertex is. It's a little bit harder to get started on plotting. So that's what the next batch of problems are going to be all about. So there it is, all scrambled. This one is, as we see it, not in vertex form. Where vertex form is y equals a x minus h squared plus k. And so it's a little bit scrambled where the actual vertex is, but that's where the good old vertex formula comes into play. It says if you have this quadratic equation or quadratic function, y equals ax squared plus bx plus c, notice again, this is also not in vertex form. then it's not too bad to still get the vertex. The x-coordinate of the vertex is x equals negative b divided by 2a. That's kind of nice. Then you can get the y-coordinate of the vertex by just substituting the x-coordinate back into the original equation. So that's what we're going to try out on this problem right here. We're going to use another trick in the next section, 9.7, called completing the square, to put it back into a vertex form. But this is just another approach. Sometimes you can use a vertex equation to still get your vertex if that's what we want. So part 1 says, find the equation of the axis of symmetry. So here's the axis of symmetry part. But borrowing the idea from the last set of notes with the vertex form, the moment you have the x-coordinate of the x-coordinate of the vertex will give you that axis of symmetry. So really, we start off by just using the vertex formula right here. We get the axis of symmetry and half of the entire vertex in one shot. So let's write this out. The formula is x equals negative b over 2 times a. B coefficient is the one that belongs to the degree 1 term. So in our problem, the b coefficient is going to be a 5. We'll take negative 5 divided by 2 times a. A in this problem is a 1, since the leading coefficient is just a 1 times x squared really. And so the axis of symmetry is the equation x equals negative 5 halves. And it's also, like we mentioned, half the vertex. So let's review what it said to do to get the other half of the vertex. The y-coordinate for the other half is found by substituting in the x-coordinate, the one we just found, back into the original equation, and that's the original equation there by the red dot. So step 2 is just a spot of arithmetic. We're going to go for the vertex. We have half of it, and now we go and say y equals, for the other half, the y-coordinate, plug back inside here what the x value was. So there's an x squared plus a 5 times x plus a 6. We're just making 2 quick substitutions. The place where x is, we put in a placeholder and throw in negative 5 halves on both. Let's expand all this out. First one is 25 fourths. Then minus 25 halves. Plus 6. It's kind of annoying with the fractions, but we can get through this pretty rapidly. We need at least common denominator 4. So the first one is still 25 fourths. Multiply second fraction by 2 over 2. So now it's a negative 50 fourths. We'll multiply this by 4 over 4 for a 24 fourths. And now the positive terms sum to 29 fourths minus 50 fourths, and we get altogether negative 1 fourth. So we're just about there. We just need to state the vertex. We often write just the variable v for vertex. And now we can see it's equal to x-coordinate of negative 5 halves and a y-coordinate of negative 1 fourth. So we did it. That's the entire vertex formula. It gave us the vertex, and we always know the axis of symmetry is just x equals the first portion there. So it's a pretty long problem. We found the vertex. For step 3, we're going to find the x and y intercepts. And then the last thing we'll do is sketch a graph using all of this information. Makes this one a pretty long problem in all honesty. I would say for a real exam scenario, this wouldn't necessarily be one entire problem. This would be more likely just broken up into different chunks. For example, finding x and y intercepts could be a whole different question on its own. So think of this as one kind of just big review problem where everything is glommed together. But x and y intercepts, that takes us back to chapter 2 when we were dealing with linear equations. So the reminder is, turns out the y-intercept is the easy one to get here. The x-intercept is going to be the sometimes more tougher one to get. But the reminder is to get a y-intercept, let's put in a little space. All you do is you set x to 0. So for y-intercepts, set x equals 0. And likewise, when it comes for an x-intercept, we do the opposite thing, set y equal to 0. Let's go for the y-intercept. It's kind of the low-hanging fruit, the one that's really easy to get right away. Y-intercept on this problem is going to be equal to, well, if you set x to 0, this is why the y-intercept is fast to get. That'd be 0 squared plus 5 times 0 plus 6. So the y-intercept is immediately 0, 6. That's kind of nice in the way. This plus 6 is just automatically indicating the x-intercept, excuse me, the y-intercept in the whole problem. Well, there's a good analogy to that. We've seen this before, where the constant term is the y-intercept when the equation's been solved for y. That was all the way back in chapter 2, the slope-intercept form. If it was y equals negative 2/5 x plus 2, negative 2/5 was the slope. That's the analog to the vertex that we're working on in this section. But the plus 2, that was also the y-intercept. That's for the same reason. If you take 0 for x, you're doing a y-intercept, which means you're putting 0 right here, wiping out this, and you're just getting a 2 altogether. So in slope-intercept form, the y-intercept is automatically identified. And then at the same exact time, for these particular forms, if it's x squared plus 5x, the 6 is also the y-intercept. Notice that's kind of tricky though, because that 2 is not a y-intercept. To get the y-intercept, you have to plug in a 0 there and then do some additional arithmetic. So it goes wrong when it's in vertex form, which is unusual and kind of interesting. But if this is all expanded out, and it's in this format, then yeah, x goes to 0 here, 5x goes to 0 here. The y-intercept value is just a 6. So that's nice. It means finding the y-intercept is really, really rapid on this one. But now to get the x-intercept, we have to do some pretty honest algebra. So for x-intercept, set y equal to 0. When you set y to 0, it's going to 0 right there, and you get 0 equals x squared plus 5x plus 6. And anything can happen on this one. We might, say, have to use a quadratic formula. And when we go to use the quadratic formula, there's really 3 scenarios that can occur. There could be 2 solutions, exactly 1 solution, or no solutions. But you know, this one is not quite a quadratic formula problem. You could use it, but you'd be using up a lot of valuable time. If you have a 5 here and a 6 here, it means the fastest way to solve this equation is to go back to chapter 6 methods and use factoring. We can factor this as an x plus 3 times an x plus 2. The plus 3 times 2 goes back to a 6. They add up to a 5. And so now in this format, we can just read off the solutions. X equals negative 3, negative 2. So back up on the top for the summary for x and y intercepts, we have the x-intercepts are negative 3, 0, and negative 2, 0. So let's take a tally of what we've done on this one. It's a lot of steps. We found the axis of symmetry. We found the vertex in step 2. We found the x and y intercepts. And then last thing to do is just sketch the graph with all the information we found so far. Really, we found 3 points and an axis of symmetry. So let's see what this looks like. The axis of symmetry is going to be more of a check on this when we take a look into everything. Our curve, our parabola, should be symmetric about this vertical line. Vertex is kind of awkward to plot, but negative 5 halves is negative 2.5. So here's negative 1, negative 2, negative 3. We're midway there. Negative 1/4 is negative 1.5. So if that's negative 1, here we're at negative 2.50, and about there, looks like it would be, say, negative 2.5, negative 0.5, 0.25 rather. So that's going to be the vertex. The leading coefficient is positive, so this is going to be opening upwards. That vertex is going to be the smallest point, lowest point. But when we open this upwards, we'll go through an x-intercept right here at negative 3. Another x-intercept, we found one right here at -2. So that actually looks about right. This is about what the picture should look like for a parabola. And -5/2 or x equals -2.5 does indeed go right through there. So we did it, folks. That's the alternate way to plot this kind of problem. We didn't have vertex form, so we broke it up into stages. Instead of saying getting four additional points, two on either side of the vertex, we just went for a different approach of getting both a y-intercept and an x-intercept. I know I noticed I didn't quite plot the y-intercept on this one, so let's make sure that actually lands on paper before we finalize this. So I have 1, 2, 3, 4, 5, 6. Slightly different scale because I'm running out of space in the vertical direction. So with that information actually included, the whole graph would look more like this. Okay, that's our first one for the day. We'll practice a couple more like these before we go into the next section. Let's pull up something from section 9.3, the quadratic formula, just to see how the next problems will go, with a particular attention to this concept right here from the discriminant. Well, any questions at the moment, getting through the first one? Okay, let's try out the others next. So same exact instructions. We're going to do three different steps, then put it all together for really a fourth step, graph the parabola with the given information. It's y equals x squared plus 2x plus 2. Not much I can do with that one. So let's start off just by going down the line. First thing we'll get is axis of symmetry. The axis of symmetry is going to be x equals some number, but we use the vertex formula from above. The vertex formula tells us the x coordinates to the vertex of this parabola is going to be x equals -b divided by 2 times a. And there's a kind of a cool way to memorize this vertex formula right here. Now that we have the quadratic formula pulled up, notice that -b over 2a is this part right here. Ignore the plus and minus. Let me try to circle it better. -b over 2a is just this part right here. So this part, x equals -b over 2a, is the x coordinate of the vertex to y equals ax squared plus bx plus c. Let's put this on notes just as a quick reminder. And maybe put it, let's see here. I guess we could just throw it right there. That came out a little huge. Okay, let's keep that quadratic formula and information on the discriminant on the back of our mind. So there it is. Let's calculate x equals -b over 2a. B in this problem is a 2, so this is a -2 divided by 2 times a is 1 again, so 2 times 1. But this is just -2 divided by 2, so it comes out as a -1. And so the axis of symmetry itself is x equals -1. Kind of a more friendly number this time. So now getting the coordinates of the vertex, step 2 here is not as bad. I think we can put it in this spot. So the vertex is what we're about to solve. It's going to be a v equals, and we need 2 coordinates. We already have one, -1 for the x coordinate. For the y coordinate, the idea was we take whatever x was, -1, plug it back here into the original equation. So y is going to be equal to -1 squared, 2 times -1 plus 2. And again, not too bad. This is a +1 when squaring, -2 plus 2. So y comes out as just a +1. And that fills out our vertex, -1, +1. I actually want to color code this slightly different just to convey the x coordinate goes here and here through substitution. So vertex is done. Next is both x and y intercepts. So let's make that our step 3 here. Not a bad idea to go for the freebie, the low-hanging fruit, the y-intercept. We set the x coordinate to 0. But once we do that, we have 0 squared plus twice 0, and the y coordinate just comes out as a 2. So y-intercept is really just inspection. This +2 always conveys down in this kind of way, provided it's not in vertex form. Then finally, for the x-intercept, the strategy for this is we set the y coordinate to 0, do the opposite thing, and we have 0 equals x squared plus 2x plus 2. This one's not as friendly as the last problem now that we're looking at it. This is a hard equation to solve. Factoring isn't going to work out necessarily right away on this. So it's a good idea to try to see what we can get out of the quadratic formula. This will have solutions, and it's going to be in one of these 3 different categories to describe what the solutions will be. So by the quadratic formula, x is -b plus or minus the square root of b squared minus 4ac divided by 2 times a. And let me finally scroll just a little bit there. So here's our quadratic formula. And we know that the discriminant is really the major thing driving what the solutions look like, how many there even are. And it's a good idea to just do that computation first anyways. It's a good way to kind of chunk this into pieces. So b squared minus 4ac in this problem is going to be, b is a 2, so it's a 2 squared, minus 4 times a is a 1 from over here, and c is a 2 from over here. But that means this is 4 minus 8, giving us a -4, which is less than 0. This is kind of a different sort of situation now out of nowhere. The moment we got negative in our discriminant, that means there's negative on the root. And that means from over here, there's 2 complex number solutions. Well, that's a problem as far as intercepts go. 2 complex number solutions means, let's go with the arrow instead. There are no x-intercepts, because x-intercepts require a real solution. If the discriminant was 0, we'd have 1 real number solution. So this would mean 1 x-intercept. And when it's positive, that's when the plus and minus actually is adding or subtracting a positive quantity. That's when there are 2 x-intercepts. So the quadratic formula is kind of interesting in a way. It suddenly out of nowhere becomes relevant in this concept, just graphing these things. Let me reformat my windows real quick here. Okay, we did this mostly for the sake of review. Let's say here, just to tie this off, there are no x-intercepts because of this part right here, a negative discriminant. But if you were doing a sketch of the plot for each little piece of information that you're pulling up, you might not have had to do this at all. You might have just said x-intercepts, none. You would have already known that information from the onset. And here's why. If we go to plot our vertex as our first thing here, the vertex was at -1, +1. Plot the y-intercept, because why not? Here it is. But already when we plot the y-intercept, knowing it's going up from the vertex, and it should be increasing because the leading coefficient is positive, meaning the parabola opens upward. So if we plot it with the information we have, the plot of this parabola looks like this. Kind of missed my y-intercept. Let me try again. Just from this graph alone, It never turns down and intersects the x-axis even once. That's why it has no x-intercepts, and we just algebraically double-checked it by running it through the quadratic formula at the same exact time. It's kind of nice to know that this stuff is all consistent in a way. It'd be weird if it wasn't. But that's 2 down. This time when we went to plot to this parabola, it was only using 2 points, but we followed the instructions to the letter. Just graph it as nice as you can with a limited amount of points. Well, let's try out to one more before we go to the next set of notes. Here's our next one to give a try on. It says find the equation of the axis of symmetry, the coordinates of the vertex, and the x and y intercepts. So it's another problem just like before, but this one is a little bit different than the others. You might have noticed that all the terms have a greatest common factor of, say, -2. We could factor on this one if we chose to. So if we factor out that -2, and no worries if you got to leave, what we're going to be left with is a 9 right here, which is a perfect square polynomial. So we could rewrite this as y equals, let me factor out that -2, leaves behind x squared minus 6x plus 9. Being left behind is now a perfect square polynomial. And so this one is pretty fast to plot. We will get y equals -2. This factors as an x minus 3 times x minus 3. So there's the perfect square. So now it's y equals -2 times x minus 3 squared. It's suddenly back in vertex form. We'll still run through parts 1, 2, and 3, but these are pretty fast now. For part 1, axis of symmetry, it's an equation x equals, and to get that value, we just take whatever the first coordinate is of the vertex. That's going to be a +3. We always take the opposite of the number we see here when we go to the vertex. So axis of symmetry is done. Part 2 is going to be the vertex. We write that as a v equals. These values then match. Whatever is here and here, we take the same exact value. And again, it comes from right over here, that -3. The thing that we remind ourselves often when we got to the stage is we always took the opposite value. But now we need a y coordinate to plug inside here. The y coordinate is actually available too because it's whatever you're adding and subtracting right here. If there's nothing there, then we can visualize it as a +0, and that's the y coordinate of the vertex, 3, 0. Now for step 3, let's get the y-intercept and the x-intercept. The y-intercept has the form, plug in 0 for x. Well, let's do that on the top equation. Because plugging 0 in for x here, it still works, but it's a little bit more arithmetic. It's much easier to plug 0 in here, get 0 plus 0 minus 18. So the y-intercept is -18. As far as the x-intercept goes, that's when we plug in 0 for y. But notice that's what's going on right here. Our vertex is on the x-axis. It's just 0, 3. And this can happen. The x-intercept is exactly the vertex itself. They've matched up. If we took the same exact steps as we would usually, we'd be plugging in a 0 for y. 0 is equal to -2 x minus 3 squared, and then we'd be solving this equation. This just takes us back to the square root method. We divide both sides by -2, is to have 0 equals x minus 3 squared. We take the square root of both sides. It'd be plus or minus square root of 0 equals x minus 3. All of this is 0. Square root of 0 is 0. Plus or minus 0 is still 0. Plus and minus, just as a quick reminder, for most situations, you need both of those values. So 0 equals x minus 3. Add 3 to both sides, and 3 equals x. So no matter how we look at this, how we visualize it, x-intercept is just 3, 0. So here's our quick sketch. Y-intercept's clear up there or clear down there at -18. So I'll emphasize quadrants 3 and 4. First, the vertex is at 3, 0. Let's go 1, 2, 3. And here it is at 3, 0. Then down 18. That's down 9. There's down 18. So here's the y-intercept. And then the rest of the graph is going to look like this. To the best of your freehand ability. This one's not great. Also, notice that my vertical direction, y-axis, is quite compressed compared to the x-axis direction, but you're allowed to do that. In fact, graphing calculators do that all the time, just to fit things inside a window often. But we did it, folks. This is the conclusions of the notes in section 9.6. And this one came out nice because we got something that actually did reduce down to vertex form. That's what the notes in the next section is going to be all about, section 9.7. So let's move into that section next. First, there's lots of information about vertical shifts, horizontal shifts, and rescaling, multiplying something by a squared. Let's go through these each in turn just to see what all this information is really saying. A great way to visualize this is through some kind of calculator system like Desmos or similar. And what I want to set up is something that's similar to each one of these. So here is y equals x squared plus k. We'll allow k to vary, but let's first set it down to a 0. So with k 0, I'm really just plotting f of x equals x squared, or y equals x squared if you prefer. And by the way, on these notes, whenever you see an f of x will just be synonymous with saying y. This is a function notation, something that's studied in pretty good detail in the next class, Pre-Calculus 1. And our book mixes in some of that notation occasionally here and there. So what does k do? It says it's a vertical shift. It says if k is positive, the parabola x squared is going to be shifted vertically up k units. If it's negative, it'll be shifted vertically down absolute value of k units. So let's see that in action. If k is, say, 2 or 3, it went up 3 units. And if we shift it down to, say, a -3, there we go, it went down 3 units. So that absolute value is kind of strange to look at, but it's just reminding us, if you said you went down by -3 units, that would have been a double negative. So the author tried to avoid it by slapping on absolute values there. So this part right here, this is the second corner of the vertex, just tells us how high or how low the vertex is going to be in our parabola. So bringing it back to a baseline of 0. The other component is the minus h. So let's go in here and put in x minus h power 2. Put in another slider for h. I want my k value to be set to 0. Let me scroll a little bit to this one. I want k set to 0. That's kind of hard to land on. There we go. H set to 0. And now if k is 0 and h is 0, we're back to f of x, or y equals x squared. We're told x minus h. This one is going to be a horizontal shift. But this one is really kind of tricky. Recall each time we took a vertex, I kept on saying, but always take the opposite value. And here we're seeing opposite as well. If h is positive, the parabola shifts to the left by h units, and this kind of hurts our brain a little bit. But that's exactly what we saw when we were plotting these using the point plotting method. So if I make h, say, a positive 2, we should see this go to the left by 2 units. Hang on. I think I got that mixed up. So I have my h positive I have an x minus h squared and an x minus h squared here. I think I have a typo in these notes. I think I was thinking x plus h squared there rather. It's kind of a silly mistake. Let's put that in red just to convey it. So if it's an x plus h squared right there, let me go plus as well. And try this out again. If I shift this to the right by, say, 2 units, we should see it go to the left. So let's see if that happens again after reconvening on the formulas. So I put in a positive 2. That's putting in a 2 here. H is bigger than 0. And yeah, now it's doing the thing that we're expecting. It went left by h units. Sorry for the quick edit in the notes there to fix that. If we say go to the left, if we make h negative, we should see it doing the opposite thing. It should be going off to the right. So let's make it negative. Let's go to, say, -3. So when we plug in a -3 here, yeah, it went right to that spot. 3 units to the right, the vertex is now at 3, 0. So that's 3 kind of transformations altogether. The last one is about that a value there. And we have a lot to say about that. If a is positive, it opens upwards. If a is negative, it opens downwards. Let's bring these back to a 0 and practice with that last transformation. Let's plug in one more thing, an a value. Study what happens when we change a. First, as a is 1, that's putting a 1 here, and we're dealing with just an x squared. And let's see what it says here. If a is between 0 and 1, it says the graph will be wider for ax squared than x squared. So that's the compression when it says it's going to either stretch or compress. So if I make it, say, smaller and smaller, closer and closer to 0, yeah, it starts to widen out. If you make it 0 itself, now it's a graph of a straight line. That's kind of hard to land on. There we go. And if you make it negative, it starts to open downwards. So let's bring it back to 1. If it says if it's greater than 1, the graph will be skinnier than the graph of ax squared will be skinnier than the graph of x squared. And that's what we're seeing what happens when this gets bigger and bigger. It gets narrower, or skinnier and skinnier. And so that's the compression in the x direction. So it's either going to compress or allow it to widen that kind of way. So those are the 3 kinds of transformations. We put them all together when we go back to the vertex form of a parabola. The vertex form was y equals a, x minus h squared plus k. Vertex is hk. This is just telling us, take the opposite values here once again. I think that's where I made my mistake with the minus when I was looking at these concepts here. It should have been a plus. I think I just carried over a minus from the vertex form. So we took the opposite here. We copied from here to here. This just tells us where the lowest point or highest point is going to be. And a is going to tell us whether it opens up or down, how narrow or wide it's going to be. So vertex form turns out to once again still be really quite important. That's why we'll try to write this one in vertex form and graph it just using that information. It says on this problem, include your vertex in your sketch, as well as 2 additional points. But this one's similar to the last question we did in the prior notes. Sometimes getting something in vertex form is really kind of rapid. Other times there's a lot of algebra we have to do. But notice what's going on with this one. It almost looks like a perfect square polynomial again, except we want to factor out a negative one from all 3 terms. So we can rewrite this as negative x squared plus 10x plus 25. If we do that, we can now express it as y equals negative x plus 5 squared. The power 2 comes out on the outside. Because this is a 5 times 5, we can just put in a plus 5 right here. Foiling this all out would give us the middle term, 10x, and the other terms as well. So now, right at this stage, we've got the vertex form in one shot. Well, two steps really, factoring twice. This is now vertex form. Let's put in a +0 just as a reminder. Now it's in vertex form. So once we have the vertex, we're going to sketch it. We want the vertex, so let's just state what it is. The vertex of this is going to be, well, remember when it's a +5, say, let's put a back to a 1, and h turns into a 5, that means it's actually going to the left by 5 units. Again, it's kind of surprising with that reversal of directionalities. So that's why we take the opposite of whatever number we have right here. So plug in -5 for x. So we take the opposite. Now, whatever is here, if it's blank or whether you put in a +0 or not, we'll get to the 0 for the second coordinate of the vertex. Then plotting the parabola is now really fast at this stage. Let's get the sketch done at this point. Go to -5, 0. 1, 2, 3, 4, 5. Here it is. And that's where the vertex will be. There's a negative sign in front, so that negative sign tells us this is going to be opening downwards this time. We just want to find what those points are going to be. Well, this point right here is -4, so if we set x equals -4, we can find a y value pretty quickly. Let's plug -4 here in the vertex form. This is the easiest place to solve this. Y is going to be negative. -4 plus 5 is just a 1 squared plus 0, but that just comes out as a -1. So if we're over here at -5, but move over to the right, it goes down, and it only goes down by 1. That's because there's really just a -1 right here for the a value. When we look at it in vertex form, a times x minus h squared plus k. But because this is a vertex, we have symmetry. If we go off to -6, we'll have another point at -1. And here's the 2 additional points. At this point, we're done putting down points. We can put in the final sketch. Let me put that point in at roughly the same height. And our parabola would look about like this. If you miss a point, just make that point a little bit bigger, unless you miss it by a lot. And we've got it, folks. That's the rough sketch of this parabola. So the reminder is, if you can get these in vertex form, a lot of the rest of the work is just really rapid. And there's a couple strategies for getting these in vertex form. One of the main strategies that we'll discuss in these notes is completing the square. Mainly because that comes up again that we mentioned before. We're going to do, as the last topic of the entire semester, discuss equations of circles, and we have to complete the square in that context as well. So here's another challenge problem. It's not in vertex form, so our first goal is to actually get it to that point by completing the square. So let's call this completing the square strategy. This time it's not a perfect square polynomial, so we have to work a little bit harder, but it's really not too bad. Just as kind of a setup to this, what you want to do as your very first step is associate the first 2 terms. The degree 2 term, the degree 1 term, so 5x squared plus 10x, and then go -4. And let me change the parentheses to a bracket since other stuff is going to happen inside here. So first associate the first 2 terms, and among those first 2 terms, pull out the greatest common factor. Whatever is here, multiplying x squared, we want to factor it out, meaning making the leading coefficient 1. So -5 factors out, leaving behind x squared minus 2x. Then leave it a good amount of space, close the bracket, and go -4. It's been a while since we completed the square, so the idea with completing the square is we have a new formula where we take b over 2, not 2 times a like the vertex formula, just over 2 entirely. and we square it. This is what's going to complete the square for this particular context. B is a -2 in this problem, so we'll take -2 over 2 and square it. So -2 just went inside here. This is really just now a -1 squared, coming out as a +1. So that tells us if we add 1, well, adding 1 breaks the equation. You don't have equality if you just add something and change the quantity on one side. But if we added 1, this is the perfect square polynomial right here. We'd be able to factor this thing. So what do we do to maintain equality right here? We counteract the fact that we added 1 by subtracting 1 at the same exact time. That means we didn't change the value numerically of what's on the right-hand side because these just cancel off. But we don't want them to cancel. We want to factor this part right here. -1 is just the extra residue that shows up when we complete the square. Just to take a look at how we did it back in section 9.2, let's take a look at this and compare methods. Let's get this window to behave. There we go. So the idea was we didn't like having a leading coefficient like -5, so that's why we factored it out. Over here, we had 0 on one side, so it was a little more forgiving. We didn't like the leading coefficient of 2 either, so we divided it out, just eliminated it. We got x squared minus 8x plus 1 when we did that. 1 is a constant, so we had to move it over to the other side. But here, we need to keep y exactly as is. So there was no moving anything to the other side. We just left the constant term outside the bracket, inside where we're completing the square. Then we took the b over 2 squared. That's exactly what we did on this section here. The b was -8. So we divided by 2, squared it, and got a +16. And we were allowed to add 16 to both sides of the equation. Well, again, we need y completely isolated, so that strategy doesn't work any longer. So what we did was we added 1 and then subtracted 1. If the number was 16, like in this problem, we would have added 16 and then subtracted 16. But then the very next step was we have a perfect square right here. That's our perfect square in parentheses, so we're about to factor it, just like we factored this one. So that was some time ago. Let's rewrite this again as y equals -5. Let me put a bracket in. This factors as a perfect square polynomial as x minus 1 to the power of 2. That -1 is the same -1 that you see right here, right before we squared it. We keep the negative sign, we take the square root of that +1, whatever it is, and -1 is still alive inside here, -4. Here's where we use the distributive law. This is going to be y equals -5 times x minus 1 squared. It can't multiply inside because order of operations says squaring takes precedence. But we don't want to multiply it inside either way because we're going to vertex form, and this is starting to look like it. Take -5 times -1 as well. That's going to be a +5, and then the -4 is just carrying down. And so now it's y equals -5, x minus 1 squared, plus 1. We now have it in the vertex form of y equals a x minus h squared plus k, which means we can read off the vertex. In this form, the vertex is hk. In our problem, the vertex below here is going to be, take the opposite of this number, so a +1, copy this number, another +1, and we're just about there. We have the vertex, we'll plot in 2 additional points. Our graph is going to look like this so far. So first here is 1, 1, our vertex. Next thing to notice is that this is opening downwards because the leading coefficient is -5. So if we move over to 2, that's setting x equals 2. We can get a y-coordinate pretty rapidly. We're just going to plug a 2 right here. That will be 2 minus 1 squared. So that's just a 1 squared. Negative 5 times 1 squared plus 1 is what we get. But that's just a negative 5 plus 1 for a negative 4. Notice what then that negative 5 is doing. We are over here at height negative 5, but when we move right by 1, we go down 1, 2, 3, 4, 5 units to reach a negative 4. And it happens to be going down because it's negative. If that was negative 3, we would have been going from the vertex, right 1, and then just down 3 units, stopping right here. So that's a pretty nice way to plot. It also tells us if we went left, we still go down 5 units, and we would land just right over here. And hey, we got a y-intercept just for free on this. This is a really narrow parabola because the a coefficient in absolute value is larger than 1. And this is what the rough sketch would look like on this one. So essentially, the moment we get it to vertex form, the plotting phase is just essentially over. We can plot these really, really fast using those tricks. Well, that's 2 down so far. Let's take a look at 1 more to see how these go. This one's kind of nasty, so if you're watching the YouTube video on this one, this is a good one to just pause it, give it a try, see how it goes. The way I would start this one off is just remind ourselves by organizing, we want to associate just the first 2 terms. 7x squared minus negative 98x plus 349. Sounds nasty, but it's not as bad as it seems. Next, we need to eliminate that 7, so we factor it out. Y equals 7 x squared, and I'm not too sure. Well, I'm hoping that negative 98 is divided by 7. So 98 divided by 7. Hey, it goes in evenly. So this will be negative 14 when we factor it out. Close the bracket clear over here to give it a little bit of space, then plus 349. Then this little equation comes into play. B over 2 squared. Got my x variable there. Don't forget the x variable. B value is negative 14, so we'll be taking negative 14 halves and squaring it. That's negative 7 squared for positive 49. So back down here, we add 49, then we subtract 49. Then associate the very first 3 terms. This is the perfect square. And on our next step, it's a distributive law. Multiply here to here. Don't distribute 7 inside, just multiply in front. X squared minus 14x plus 49. You can factor that right on this step down here if you preferred. Then take the 7, multiply it to clear over here. Let me make that arrow slightly less obnoxious. There we go. Another large number. So negative 49 by 7 gives us negative 343. So that's going to be negative 343 after distributing plus 349. 349 gets cut down to size, so that's kind of nice. And now we have y equals 7 times x minus 7 squared. That minus 7 you can think of as just dividing the 14 by 2. Well, that's just the same negative 7 over here. Or we can think of it in these terms. The negative sign always comes down. You take the square root of the 49 and you get the 7. So there's really 3 great ways to think about it. I think dividing the negative 14 by 2 is a clean way to think about it. So just divide by 2, and that's a guaranteed factorization. You can expand this out using the FOIL method if you prefer, just to double check your work. But it's nice to know it's a guaranteed if we did everything right. These terms are like terms, adding up to a positive 6. And now it's back to vertex form. That deserves an exclamation mark because that tells us we're basically there. The vertex for this parabola, as nasty as this looks, is going to be v equals, take the opposite of the very first coordinate, so it's a 7, copy the second value here, so it's a positive 6 for the second coordinate, And we did it, folks. That's our vertex, right at 7, 6. So 7, 6 is pretty high up there. The leading coefficient, A, is 7, tells us it's opening upwards. So let's draw a graph that looks like this, emphasizing this time quadrants 1 and 2 more than any others. Here's 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. So that's the vertex. The 7's positive, so it's opening upwards. Let's use that trick again. Here's 7. If I go up to an 8, we just have to go to here where it was height 6 and add 7 more units. Why add 7 more? It's because that's a positive 7. So go up 7, 8, 9, 10, 11, 12, 13. So 8, 13, right up here, it's automatically one additional point. We get for free 6 is now at height 13 as well through the axis of symmetry, the concept we were practicing in the last section. And so as fast as possible, this is a great way to sketch a parabola. Vertex and 2 points is going to tell you the shape. Knowing the direction it's opening is going to give you how high you get to the next points. And if you ever forget that trick, it's not so bad either. Wherever you are at the vertex, pick one number to the right or the left. Let's pick x equals 8. Plug it in for y. You could plug it in here and just crank it out in the calculator. But plug it in for x rather. Plug in 8 for x here. It's easier to plug it in on the one where it's in vertex form. The arithmetic's easier. You get 7 times 8 minus 7, which is just a 1 squared plus 6. But then 7 plus 6 is 13. So we get the 13 either way. And it didn't matter if you plugged in an 8 or if you plugged in a 6. Plugging in a 6 would have given us a negative 1 squared, but negative 1 squared is still a positive 1. You'd still get a 13 either way. It's that power 2 really that's giving us the whole symmetry through the axis of symmetry in this problem. Well, that's kind of half the topics that we're going to be looking into section 9.7. The other half is if you want to really get good at understanding these kind of graphs, you have to be able to reverse engineer this. Seeing a graph, we should be able to write down the equation in vertex form like we just saw here. And so that's what we're going to be doing on the next examples. So let's take a look at the next two. For just the sake of thinking of these concepts again, I recopied in just the properties of the vertical shift, the horizontal shift, and the rescaling. That's a great way to think about this because when we look at the parabola down below, let me see if I can move it up just a touch. Not easily. Let me just zoom out a touch. When we look at the parabola down below, it's kind of like y equals x squared. Only thing is it's been moved vertically up 2 units. That's a vertical shift. It's also been moved, oh, let me fix that to a plus as well on this one. It's an unfortunate typo. Let's make a correction there. It's also been moved to the left to, this is -2, so -4. So it's just been moved around. Let me fill in those numbers there. So that's 4, and this is -4 on that coordinate. Well, we can say the vertex is then immediately -4, +4. And if I move over to -3, looks like it moves up to 1, a value of 5. That means A is probably 1 on this one. But sometimes our eyes can be kind of deceiving on this, so we'll double check it. A is definitely going to be positive because it's opening upwards. So if we were going to find the equation in vertex form, we would first write out y equals a x minus h squared plus k. So this is the vertex form we're going for. But then these numbers get mixed in with h. This number gets mixed in with k. And we can say now y equals a x plus 4 plus 4. So same concept as before, that -4, we plug it in for h, but then it's double negation, and it turns into a +4. The big idea is we always take opposites, no matter how we're solving the problem. These are always opposite. But the k value here, that's strictly copying from here to here. Doesn't matter which direction we're going, these are always copied. We're almost there. We just need to discover what is the a coefficient. It's probably a 1, but we're eyeballing it at that time. We're eyeballing it in that sense, rather, if we think it's a 1. So here's another great way to check. If we can get another clean and obvious point on this graph, that'll allow us to solve for y. I wouldn't want to grab a point out here because I don't know what the exact coordinates are. I know this is at height 6, but I don't know the x-coordinate too well. But this point right here looks like it's at -2, +8. So using those values, this is when x is -2, y equals +8, we can plug both pieces of those information in for y. So put 8 here equals -2 for x over here, and then +4. Oh, and don't forget to put in the a in front. Let me try again. So first, h for y equals a, that's what we're solving for. Plug in -2 for x, +4. Looks like I forgot the power 2 there, so don't forget the power 2 as well. +4. And then let's just solve this equation down here for a. This becomes 8 equals a times, this is a +2 squared, so it's just a 4, +4. Subtract 4 from both sides, and 4 equals 4a. Divide by 4, and 1 equals a. So our prediction is correct. We're at the vertex and we move right 1. This is at -3. We should be going up 1. This looks like it's at +5. That alone told us probably more likely than not, a is 1. But if you're ever not sure, this is a great way to check. Just get 1 point on the graph. Here it is, 8, 4. Excuse me, 8 and -2 is that point. Plug it into this equation over here for y and x, and then just solve for a. So after all this work, our answer for the equation in vertex form is, if a is 1, we don't have to write in anything at all. It's x plus 4 squared plus 4. Let's put a box on that since our work is kind of everywhere this time. So that's 1 down, and we'll just do 1 more to complete the notes. And that'll be it for us today after we complete the next one. So here's the next one to take a look at. Let's see, another graph. This time it's opening downward. The vertex is at its highest point. Let's write down the coordinates for this. Vertex is at points. Well, it looks like these are kind of an inconvenient scale. This is at a height 1. This is a 3. So that would be at a height 5. That's a second coordinate. This is at -1, -2. Here's -3. And then -4 is the x-coordinate. So the vertex is at -4, 5. Once we identify the vertex, we just write out y equals a, x minus h squared plus k. Whatever is here, we plug in there. Whatever we find here, we put into that position. So now we have y equals a, x. This will be a +4. Plus a 5, and power 2. So one more time, just so we can recall the way these go. This always copies in either direction we're going, whether we're writing it in vertex form or going from vertex form into the vertex. And this one is always, each and every single time, the opposite. So if we had a vertex at -4, that means in vertex form, we should have an x plus 4. After doing that, well, we need to solve for a, and all I can tell you for certain is that, well, a is negative because the parabola is opening down. But here's our trick when we're plotting on the next ones. If you move over right by 1 unit, so you're at -3, and just see how far down you went, that will tell you what the a value is. So let's use that trick and then do it algebraically as well, just as a double check. So move right by 1. We're at -3 for x at this coordinate, and we'd be moving down 1, 2, 3 units to get to this next point. This strongly suggests a is -3. So the whole answer is then y equals -3, x plus 4 squared plus 5. And if you feel confident using that shorthand of a trick, then the problem is over. But if you want to be extra sure, say there's extra time on an exam, you want to really check this out, here's what you need to do. Get coordinates of that point. They're at -3, +2. This means x equals -3, y equals +2. Plug that information into y and x, and then just solve for a. So if we did that, we'll have 2 equals a times -3 plus 4 squared plus 5. Again, substituting it in here where it's highlighted in yellow. Doesn't hurt to re-highlight these to show where we substituted. Now we have a nice equation where we can solve for a. -3 plus 4 is just a 1 squared. So this is 2 equals 1 times a for just an a plus 5. Subtract 5 from both sides and we get to -3 equals a. And that matches our geometric way of looking at it as well. So it's kind of nice to have two different approaches. The algebraic approach is nice and slick and always works. It requires you find an exact coordinate, but so does the counting approach. I had to know that when I went to right 1, I'm going down 1, 2, exactly 3 units to land on that specific coordinate there. Well, we did it, folks. That's going in the opposite direction, taking the graph of a parabola. Vertex form has a lots of great uses because we can use that vertex form to just build out the equation of that parabola. Well, when we come back after the break on Tuesday's class, the main thing we're going to be working on next is applications, optimization. And the thought is, when we were in section 9.5, this was before the exam, we were looking at one particular application that did result in a parabola. Scroll down to it. Here it is. The height of an arrow being shot vertically upward gave us this. There's a time axis and a height axis. And you know what? That's a parabola with a coefficient, that leading coefficient, that was negative. Here it is, the -16t squared plus 220t minus 400, before we divide by -16, changing its sign. If we can find the vertex of that, that's pretty quick. We just use the vertex formula. We would know the time at which the arrow reaches a maximum height. So that's where the information connects with these graphs. They're going to start having meaning of some kind. And we're going to be looking into some optimization topics, finding maximum values like in this graph, or finding minimal values like in this graph where the vertex is the lowest point. But this is definitely a good stopping point for us. I ran out of material at this point. We'll come back to this after the Thanksgiving holiday, so have a great holiday, folks. If you have any questions over the Thanksgiving break, don't hesitate to write. I'm still going to be checking my email, and so I'll be happy to get back to you. I typically check first thing in the morning, so I'll get back to you at those times. Take care, and I'll see you.